Hi everybody, welcome back. In this video we're going to demonstrate how to implement the gradient descent algorithm that we introduced earlier in this module. Gradient descent is an optimization technique that is used extensively in machine learning and deep learning to minimize the loss function. The algorithm is based on an approach in which the gradient of the loss function is used to iteratively adjust the model parameters in the proper direction to minimize the loss. As we'll see further below in this notebook, this technique leads to an intuitive and simple update equation that is used to find the optimal parameters of a model. In this notebook, we're specifically going to take a look at how to fit a straight line through a set of data points to determine the slope of the line, and we'll be using gradient descent to implement this. As summarized in the outline below, we're going to first take a look at a brute force search, and then we'll also review 3 different versions of gradient descent. One of the main benefits of a brute force search is that it enables us to visualize the loss function and also provides a very intuitive basis for describing how gradient descent works. So let's go ahead and get started, and the first thing that we're going to do is create a convenience function that's going to generate some data for us. We're going to start by setting a random number seed in the notebook so it's repeatable, and then we're going to call the uniform function to generate 30 data points in the range from 0 to 1, and then multiply those by 10, which will expand the range to be from 0 to 10. And then next we're setting the y values to be equal to the x values with just a small amount of noise added. So in effect, we're generating a set of data points that are based on a model of a straight line that passes through the origin with a slope of 1. And even though we've added some random noise, we would expect the solution for the slope to be very close to 1. Also notice here that we're starting to introduce TensorFlow variables rather than just NumPy variables in order to start getting more familiar with using them. So now let's take a look at using this function. You can see here on line 2 that we're calling the function, and it's going to return x and y values for us, which represent the data set that we'll be working with in this notebook. And then here on lines 5 and 6, we're computing the min and max values of the independent variable from this data set, which enable us to create a line on the plot with a slope of 2, which represents our initial guess for the line that fits the data points shown in the plot below. As we'll see further below in the notebook, we'll be using gradient descent to modify the slope of the line to improve the fit. So before we implement this in code, we're going to formalize the mathematical model and also define a loss function. The model we've chosen is simply given by y equals mx, where m represents the single unknown parameter that we'd like to solve for, which is the slope of a line that passes through the origin. So for any particular point, the error is given by the ground truth for that point, which is yi, minus the quantity mxi, which is what the model predicts for the y value. And since we don't care about whether this quantity is negative or positive, we're going to square that difference and then sum the errors across all the points in the data set. And this now becomes the loss function that quantifies the total error for a given value of m. This particular loss function is referred to as the sum of squared errors loss, but there's 2 other familiar forms shown below, which are mean squared error loss and mean absolute error loss. In the remainder of this notebook, we'll be working with mean squared error loss for demonstration purposes. Let's now take a look at how to perform a brute force search to find the value of m which minimizes the loss function. The basic idea here is that we're going to scan through a range of values for m, and for each value of m, we're going to compute the loss, and then we'll select the value of m associated with the minimum loss. In this first section of the code below, we're going to set up the parameters for our search, which include 50 different values of m that straddle the actual value, which we know to be 1. And then here we're going to initialize 2 TensorFlow variables for both the slope and the computed loss so that we can save those values and plot them. Here in this for loop, we're going to cycle through all the values of m, and for each value we're going to compute the error for each data point given by e. On the following line, we're then going to square each of those errors and compute the mean squared error for the current value of m, which is now a single number that we're going to store in the loss tensor. So now once we've cycled through all those candidate values for the slope, we can use the argmin method in TensorFlow to determine the index associated with the minimum loss, and then we can use that index to determine the corresponding slope for that minimum loss. And then here we're converting that to a NumPy variable called m_best. And then further below, we're plotting the loss as a function of m, and this now gives us a very nice picture of what the loss function actually looks like. And as you can see, the best value of m corresponds to 0.98, which is pretty close to the actual value of 1. If we had chosen a finer granularity for the slope, we certainly could have done much better, but this just demonstrates how you can use a brute force search to minimize a loss function and determine the value of your unknown parameter. So now that we have a value for the slope, we're going to create a convenience function that we're going to use several times in this notebook that's going to allow us to plot our data points and overlay those data points with our model of the best fit line. So this function has 3 required arguments. The first 2 represent the x and y coordinates in our data set, and the third argument represents the value of the slope for the fitted line. And then optionally, you can also specify the x and y plot limits. So as you can see in the plot below, the model fits the data quite well as we would expect. So now that we have a good feel for what the loss function looks like, let's continue on with a description of how the gradient descent algorithm works. Since the loss function is convex, meaning that it has just a single global minimum, intuitively, if you're at some point on the loss function that's not at the minimum, you can see that the slope of the loss function can inform you as to what direction you need to move in along the x-axis in order to find a value of m that has a smaller loss. We can do this by computing the gradient of the loss function with respect to m, and if that value is positive, which would correspond to a point on the loss function which is to the right of the minimum, we know we would need to adjust the value of m some small amount to the left, and if the value of the gradient is negative, then we would need to move some small amount to the right. So intuitively, you can see that the update equation that's shown here makes perfect sense, and the only question is how much do we need to adjust the value of m? And so that's where the learning rate lambda comes in, which is a tunable parameter that we need to specify, which is a value less than 1 that attenuates the gradient. Choosing a proper value depends a lot on the specific problem, but as a general guideline, values might range anywhere from 1.e to the minus 2 to 1.e to the minus 4. If the learning rate is too large, then we can overshoot the minimum in either direction, which could result in diverging behavior. And on the other hand, if the learning rate is too small, then it can take quite a long time to get to the minimum. So this is one parameter that comes up again and again in deep learning, and as we progress through the course, we'll see that there are capabilities within TensorFlow that allow us to adjust the learning rate automatically. So let's now take a look at the implementation for gradient descent. Since this is an iterative algorithm, we need to specify the number of iterations we're going to consider. We don't know in advance what number is suitable, but for this example, we're going to start with 50 iterations, a learning rate of 0.005, and an initial guess of 2 for the slope of the line. Here we're creating a TensorFlow variable to store the loss for each iteration so that we can plot the loss history further below. And then here in the for loop, we're going to compute the gradient based on the current value of m. And notice that this is done for all the data points, which is one reason why this technique is also referred to as batch gradient descent, because we're processing a batch of data. So the value, and more specifically the sign of the gradient, is now going to inform us in what direction and how much to adjust the value of m. And then once we have an updated value of m, we're going to compute the loss associated with the updated value and store that so we can plot it further below. The best value of m is simply the value of m that we end up with after executing all the iterations. So you can see that the learning rate and the number of iterations can have a significant influence on the final value of m, but it's often very instructive to look at the shape of the loss curve to determine if more iterations might be required. This is an oversimplification because there's other factors that come into play, but we just wanted to emphasize that the training process typically requires a lot of parameter tuning and experimentation. As you can see in the first plot below, the loss comes down dramatically, which is fairly typical, and then by 30 iterations there doesn't seem to be any change in the loss, which is an indication that we've reached the minimum, and therefore the value of m after 30 iterations isn't changing much at all. And then taking a look at the second plot, the best fit line has a slope of 0.998, which is extremely close to 1 and fits the data very well. So let's now move on to stochastic gradient descent. In the example we just demonstrated above, we used every single data point from the data set in order to compute the gradient of the loss function. But in many real-world applications, we may have millions of data points to evaluate, so calculating the gradient based on all available data can be very computationally expensive. So a logical question to ask is, do we really need the entire data set to compute the gradient at each iteration in this process? And the short answer is no. What we need is a good estimate so that we can move in the right direction. And to make this point, we're going to now run the same experiment, computing the gradient using just a single randomly selected data point at each iteration. And we'll see that using a single data point is enough to get us going in the right direction. This won't be as accurate as using all of the data points at each iteration, but it can still be very informative. So the only difference between this implementation below and the prior example is that in the code below, we're going to randomly compute an index in the range of the number of data points, and then we'll use that index to access the data point to be used in the gradient computation. And other than that, the code is exactly the same. As you can see in the plot below, the loss function comes down a little slower, not quite as smooth, and not quite as low, but after about 20 to 30 iterations, the loss bottoms out, and in the end, we achieve a slope of 1.004, which is about the same accuracy achieved with gradient descent when we used all the data points to compute the gradient. In practice, stochastic gradient descent won't compare quite as well to gradient descent, but this leads us now to the next section called stochastic gradient descent with mini-batch, in which we're going to make a compromise and use what's known as a mini-batch of data. And again, the idea here is if we have a very large data set, we don't want to spend a lot of computational resources on computing a gradient using all of the data, but would like to select a random subset of the data so that we can get a very good estimate of the gradient with much lower computational cost. Because the estimate may not be quite as good as using all the data, we would expect a larger number of iterations to converge, but that will be offset significantly by the reduction in resources required to compute the gradient on just a mini-batch. In terms of the code implementation below for using a mini-batch, it's nearly identical to stochastic gradient descent, except this time we're setting a batch size of 10, and instead of randomly selecting a single data point, we're randomly selecting 10 data points. And then additionally, since we're computing mean squared error loss, we need to divide both the gradient and the loss by the batch size. And now when we take a look at the results, you can see that they're very comparable to gradient descent, both in terms of the final accuracy and also the number of iterations required to minimize the loss. To better appreciate these three separate cases, we've plotted all three loss functions in the next section below on the same scale so that we can make a side-by-side comparison. You can see that gradient descent and stochastic gradient descent with mini-batch are very comparable, while the middle plot for stochastic gradient descent doesn't perform quite as well, which is expected since we're only using a single data point at each iteration. In the final section of this notebook, we're going to take a look at the automatic differentiation capability within TensorFlow called Gradient Tape, which is a lower-level API that performs auto-differentiation on defined operations and variables. As we'll see in future videos, TensorFlow provides a built-in capability to train neural networks using the compile and fit methods in which you specify which optimizer you'd like to use. Since the optimizers in TensorFlow implement backpropagation using gradient tape, it isn't often required to use gradient tape explicitly, but there are times when more advanced modeling is required in which we'll need to access lower-level APIs within TensorFlow such as gradient tape. So in this section, we're going to introduce the use of gradient tape with some very simple examples, and then we'll demonstrate how it can be used to compute the gradient for the gradient descent algorithm, and then we'll also revisit this topic in more detail in future videos. The general idea here is that you create a gradient tape context, which is a Python scope that will automatically record every operation that involves a trainable variable. By default, any variable created with tf.variable is a trainable variable. You can then use the tape reference to call the gradient method to perform the gradient on the operation with respect to one or more trainable variables. So in this first example, we're creating a TensorFlow variable called x, and then we're going to define a gradient tape context called tape. And then within this context, we're going to define the operation y equals x squared. And then once we've set this up, we can then use the tape reference to call the gradient method to compute the gradient of y with respect to x. So when using this, we don't need to explicitly define the gradient. We simply need to specify the computation, which is y equals x squared, and then the differentiation is taken care of for us automatically. And as you can see below, we get the expected result, which is 8, since the gradient of x squared is 2x, and with the value of x equals 4, the value of the gradient should be 8. In this next example, we're going to create two TensorFlow variables, w1 and w2, and then we're going to define a gradient tape context with an operation involving both variables. By default, the resources held by a gradient tape object are released as soon as the gradient method is called. So if you need to compute multiple gradients, as in this example, then you need to create a gradient tape context with persistent equal to true, as we've done here. And then after we compute the gradients, we can delete the reference to the tape manually using the delete command. And as you can see below, we get the expected results for each of the gradients. So now we're going to conclude this notebook by showing that we can use gradient tape to implement the gradient descent algorithm. And the only difference in the implementation below is that we're creating a gradient tape context where we define the loss function within that context. And then on the very next line, we're using the tape reference to call the gradient method on the loss with respect to m. And then everything else below is identical to the previous example. And as you can see in the results below, we get the same value for the minimum loss and the best parameter as we did further up in the notebook. So that's all we wanted to cover in this video on gradient descent. In the next video coming up, we'll introduce the topic of linear regression, which offers a nice context for introducing the mathematical framework for traditional supervised machine learning problems, which can also be casted as simple linear neural networks, which serve as a nice transition to the next module coming up where we'll introduce deep learning neural networks.